Hi all, welcome to this lecture 9 of Unconstrained Optimization lecture series. Today's lecture is on convex functions, and we'll continue our discussion over convex function from the last lecture. So before we begin with our today's lecture, we'll just recall a few of the definitions and the things that we covered in the last lecture. So we'll start with convex functions definition. In convex function definition, so let's see be some subset of n-dimensional real set, and let it be a convex set. The convex set is basically a set in which if you have 2 points, if you take any 2 points and the line segment joining those 2 points, all the points on that line segment is inside the convex inside the set, then the set is convex set. So if C is a convex set and a function f from C to R is said to be a convex function, if any 2 points x1 x2 in that set C, and for some lambda real number between 0 and 1, this condition is true. So what does this condition say? That some linear combination of those points such that this point is on a line segment between these 2 points is smaller, the functional value is smaller than is below that line. So graphically we can see if we have 2 points A and B, and let's say this is the point C given by lambda A plus 1 minus lambda B, then this point will be higher than the point on the graph itself. So this is the definition of a convex function. We also discussed what is an epigraph of a function. So let x be a subset of n-dimensional real number set, and f be a function from x to some real set R. So we can always describe a function f by its graph. So basically it's the graph belongs to a set of Rn plus 1 in which we plot x, the vector, the input vector, and fx, the output vector. The epigraph of f is a subset of Rn plus 1, and it is defined by x comma y, a locus of points x comma y in which x belongs to the input set x, y belongs to the output set R, and y is greater than fx. So basically all the portion of the graph which is above the graph of the function is the epigraph. So as you can see, all the portion of the graph which is above the graph is an epigraph. Now we also learned that if a function is convex, if some function f is convex, then its epigraph is a convex set. We got an intuition of this set. So let's say if we have 2 points, so we can see that the function is non-convex here because some of the points between 2 points on the line is below the function, and so we can see that the epigraph is not a convex set. But here if you can see, there's a convex function, and if we draw a line, it lies within the epigraph. So epigraph can be said to be it looks like that epigraph is a convex set. Now let us continue the discussion, and let's see this result that we discussed just now in a more formal way as a theorem and try to prove it. So let's write our first theorem of the day, that is, so I'll first state the theorem and then I'll try to explain it, and then we'll prove the theorem. So let C be a subset of Rn, be a convex set, and f be a function from C to R. Then f is said to be or f is a convex function if epigraph of f denoted by epf is a convex set. Just to correct my mistake, this is if and only if. So what this theorem says that if f is a convex function, then epigraph is a convex set, and if epigraph of f is a convex set, then f is a convex function. So it's to and fro. So what does this say? If f is convex, double implies epigraph of f is, if f is a convex function, let me just write it properly. So if f is a convex function, then epigraph of f is a convex set, and vice versa. So this is what this theorem is saying. So we have understood what the theorem is saying. Let's try to prove it. So as you know, because it's if and only if, this will be proven in two parts. So let's look at the proof of the theorem. So let's first assume that this is the first part. Assume that f is convex. F is convex function. All right. So f is a convex function. So let's take 2 points in the epigraph. Let x1 comma x2 or x1 comma y1 and x2 comma y2 be 2 points in epigraph of f. So by definition of epigraph, we can say that y1 is greater than or equal to fx1 and y2 is greater than or equal to fx2. So this is by the definition of epigraph. Okay. Now because f is convex, for some lambda between 0 to 1, we can write this property, the inequality which defines the convex function, that is lambda x1 plus 1 minus lambda x2 is less than equal to lambda dot fx1 plus 1 minus lambda dot fx2. Okay. Let's mark this as 1. Now by 1 we can write this as f lambda x1 plus 1 minus lambda x2 smaller than lambda dot y1 plus 1 minus lambda dot y2. Correct? Now, by this statement, we can say that lambda dot x1 plus 1 minus lambda dot x2, comma lambda dot y1 plus 1 minus lambda dot y2. This point belongs to epigraph of f for all lambda belongs to 0 comma 1. Why that is? Because you can see that all the points for which the function value is less than the function value is less than those values, then this is the definition of epigraph itself, right? So by this we can say that this belongs to epigraph of f, which means, and if you look this lambda x1 plus 1 minus lambda x2 and lambda y1 plus 1 minus lambda y2 is actually the line segment. So if lambda goes from 0 to 1, this represents a line segment from x1 y1 to x2 y2. So this implies that line joining any 2 points on an epigraph lies inside epigraph. So what does this say is that if I have 2 points x1 comma y1 and x2 comma y2 in the epigraph, so these 2 points are in the epigraph, any point on this line which is represented by lambda dot x1 plus 1 minus lambda dot x2 comma lambda dot y1 plus 1 minus lambda dot y2, any point lies on the epigraph, and this is true for any x1 and y1 and x2 and y2 in epigraph. So what does this means? That epigraph is convex. Correct? So we assume that let f is a convex function, and then we prove that epigraph is a convex set. So first part of it is proven, that is, if f is convex function, then epigraph of f is a convex set. This has been proven. Now let's prove the other part. The second part. So in this part, let's assume epigraph of f is a convex set. Okay, now we'll assume one thing. We'll again assume 2 points. Let x1 and y1 and x2 and y2 be 2 points on the graph of function fx, graph of function f. Okay, so let these 2 points be a part of function fx, so which actually means that x y1 equal to fx1 and y2 equal to fx2. Okay, now because all the points on the graph of f are also part of epigraph, we can say that so let's say this is these are 2 points. Now these 2 points are also in epigraph. Okay, and because epigraph is a convex set, we know that all points in the middle of these 2 points should also be in epigraph. So we'll write that. So lambda x1 plus 1 minus lambda x2 comma lambda y2 I'll directly write lambda f1 fx1 plus 1 minus lambda fx2 belong to epigraph of f for all lambda belonging to 0 comma 1. So here it is a closed interval, because for 0 and 1 x1 the points become x1 and x2 for lambda 0 and 1, and they are inside the epigraph. Now we also know for a fact that because this point is in epigraph, by using the definition of epigraph, we can write lambda dot fx1 plus 1 minus lambda of fx2 is greater than equal to f of lambda of x1 plus 1 minus lambda of x2, which implies that f is convex. Hence, we have proved that if if epigraph is a convex set, then f is a convex function. So both the parts of the theorem are proved, and hence the theorem is proved. Okay. Now, before continuing, I just want to share a quick fact with you all. So let's say this is a function. So you might know this function as modulo function or absolute function, in which so this is the epigraph. So as you can see, the function is not differentiable at this point. But is the function convex? The answer is yes. Is f convex? The actually answer is yes. And it's you can also see that its epigraph is convex set. Epigraph of f is a convex set. So a function need not be differentiable in order to be a convex function. So a convex function need not be differentiable. Okay, so this is a quick fact that I wanted to just share with you all. I hope this is very obvious, but I just wanted to state it once. Now we'll continue on the next definition, which is level sets. So I'll state the definition, and then I'll explain the definition of level sets. So let C be a subset of Rn, and let C be a convex set. Let f be some function from C to R, and let f be a convex function. Then level set of f for a given alpha is defined as C alpha x belongs to C such that fx is less than equal to alpha for some real alpha. So this is the definition of level sets. So let C be some convex set and f be some convex function. then the set which is defined such that fx is less than equal to alpha, all the points which which follow this inequality belong to the level set C alpha. No, notice that C alpha is a set. It's not a function. It's a set. It's a collection of points. So, so for example, in one dimensional, if I want to give you some intuition, let's say C is this. C is this set from A to B, okay, and this is alpha, okay. So all the points of fx such that fx is less than this alpha, let's call them A prime and B prime, then A prime comma B prime is C alpha. Okay, so this is what level set means. So if you have been given some real number alpha, then the level set can be defined using that. So I'll just say that there is a very important result related to level sets, which we'll discuss now. So we'll discuss it as a theorem. So if f is a let me change the color of the font. I think it's not visible. If f is a convex function, then the level set C alpha is a convex set, is also a convex set. So it's a very straightforward theorem which says that if f is a convex function, then any level set C alpha is a convex set. So if you define any level set C alpha according to the above definition, then they all are convex. They are all convex sets. Okay, so please note, this theorem does not say that if all the convex set, all the sub levels, all the level sets of function f are convex, then f is a convex function. It does not say that. So it's single implies. So the theorem says that if f is convex function, implies all level set C alpha is a convex set. For all alpha. So for all alphas, C alpha is a convex set, where C alpha means level set. The reverse is not true. So there is no if and only if condition here. So now let's prove the theorem. So first let's assume what is given. So let f be a convex function. Let f be a convex function. Now let x1 comma x2 be 2 points in level set C alpha. Okay, what does that mean? That means f of x1 is less than alpha less than equal to alpha, and f of x2 is also less than equal to alpha. Now because f is convex, function, what can we write? Lambda times fx1 plus 1 minus lambda times fx2 is less than equal to, or sorry, is greater than equal to f of lambda dot x1 plus 1 minus lambda dot x2 for all lambda belonging to 0 to 1. This we can write. Alright. Now from 1, so let's call this condition 1. Both fx1 and fx2 are less than alpha, implies if we can convert this into lambda dot alpha plus 1 minus lambda dot alpha is less than f lambda dot x1 plus 1 minus lambda x2. Okay, we can write that, which you can see lambda alpha gets cancelled and what remains is only alpha. So alpha is greater than f lambda dot x1 plus 1 minus lambda x2. Okay, which is actually the functional value for any so this is true for all lambda belonging to 0 to 1, right? So this is a functional value of all the points which are on the line joining x1 and x2. Okay, x1 and x2. So all the points between x1 and x2 on the line are also a part of C alpha. You can see because they follow this property. So which means lambda dot x1 plus 1 minus lambda dot x2 comma so this belongs to that's level set C alpha. What does the which means that C alpha is convex. I hope you got it, because this this condition tells us that all the points between x1 and x2 that lie on the line x1 joining x1 fx1 and x2 fx2 are also in the level set C alpha, because they follow this property of functional value less than alpha. So, and this is true for all alpha and any arbitrary point x1 and x2. So this is true for all points in C alpha. So C alpha is convex. So it was a simple proof. Now let's move on, and let's move on. And before moving on, I'll just the thing that I discussed, I'll just want to reiterate it here, that converse of this theorem is not true. Okay, that is if every level set of f is convex, is a convex set, then it is not necessary that f is a convex function. It's not necessary that f is a convex function. Can you think of some example for this? So very good example or very common example is the function fx is equal to x cube from, so f is from r to r, single valued function, single real valued function. So this is the function. So if you look, then, but this every level set is convex. So for this every level set is convex. So if the value is some alpha, so it's actually minus infinity to alpha. So this is a convex set, okay, and but the function is not convex. So fx is equal to x cube is not a convex function, because you can see if I put 2 points here and here, the line is above the function in some points and below the function in some other point. So this is not a convex function. So the converse of the theorem is not true. Okay. So let's discuss some properties related to that can be related to this theorem. And let's define, before going on, let's define some sets such that h of x is less than equal to 0. Let's say this is some set, and let's say hj is a convex function. Let's say h is a convex function. Okay, so h is a convex function, which means this is a convex set. Okay, so this, the sets following all the x which follow this property forms a convex set. Let's say there are a series of hj's like this. So all of them are convex, and j varies from 1 to m, let's say. And then there are some equality sets which follow the equality. So let's say ei x is equal to 0. So, and let it be convex. So it turns out a set which is represented by an equality can be convex only if it is an affine function. If the left hand side ei is a affine function, or basically it's linear in nature. Okay, so that is true, and then I going from 1 to l, etc. Okay, and let's assume these to be constraints, and above that let's form an objective function fx such that fx is a convex function. Okay, subject to these two constraints, some inequality constraints which are convex, where h is convex, and ei linear constraints which are also convex. So these kinds of programming problems are called convex programming problems. In which the objective function is also is convex, and the constraints are also convex sets. Okay, now let's look at some examples of such problems. Some examples of such problems. So the first one is a linear objective function subject to some linear inequality constraint. Okay, so graphically it will be represented by something like this. So these are constraints basically. So this x such that ax is less than equal to b. This is a feasible region, and let C be this line. Okay, represented by this line. It turns out, just by intuitive reasoning, you can say that this will be the point with which will be the solution, like which will be the minimum. How is this the solution? We'll get to it later, but if you think just by some common sense or regular logic, you'll be able to find that, let's seize this vector. Okay, so you'll be able to find that the minimum will occur, given these conditions, will occur at this point. Now, we'll have there is other example where we can have quadratic functions like half x transpose h x minus c transpose x. Okay, subject to ax less than equal to b, some linear inequality constraints, where h is symmetric positive definite. So symmetric positive definite. So this is a convex programming problem. It turns out that if h is a symmetric positive definite, this becomes a convex function. And how will look, and this is anyways a convex set. So that's the thing. Another example can be minimize x1 plus x2 and subject to constraint that x1 square plus x2 square less than equal to 1. So by visually you can see that this constraint mean that the feasible region is inside a circle of radius 1, and x1 plus x2 is some line going from here to here. Okay, so, or sorry, x1 x2 can be some line like this. So C is in this direction, x1 plus x2, and you can see that just by previous logic, the global minimum will be at this point. Just by logic you can see that because x1 and x2 is there, and the maximum value will be where both of them are negative. So x1 and x2 both are negative, so it will lie in this quadrant, and by some basic technique you can come to conclusion this will be the where this C is perpendicular to the circle. At that point this will be a minimum. How we get this point formally we'll discuss later, but in constrained optimization lectures we'll discuss, but I think this is fairly clear here. Till now we have not considered the differentiability or twice differentiability of the minimizing functions, but it turns out that if we assume differentiability or twice differentiability, there are many more results that can be useful for our analysis. So let's try to look at this properties of differentiable or twice differentiable convex function. Okay, so there's if a function f is convex and it is differential or twice differential, there's certain results that will help us identify that the function f is convex. So based on that, I'll just start with the theorem, and then first I'll state the theorem, then I'll explain it, and maybe I'll give a geometrical interpretation of the theorem first, and then we'll prove the theorem. Okay, so yeah, so let C be a subset of Rn, be a convex set, and f from C to R be a convex function. Sorry, be a differentiable function. Okay, now let g of x represent the first differentiation, the gx represent the first derivative of fx. Okay, so the first derivative of fx, then f is convex if and only if, please note it's an if and only if fx2 is greater than equal to fx1 plus g x1 transpose x2 minus x1. So if this inequality is true for any 2 points, then f is convex, and if f is convex, then this inequality is true.
So last a close one.
And this is for all x1 comma x2 belongs to C, some set C. So this is the theorem. Further, if f is a strictly convex, if the above inequality is strict for all x1 comma x2 belonging to C. So is that x1 not equal to x2? This is if and only if also. So this is the theorem. First, let's see what this theorem represents geometrically, and then in that way you will be able to understand what the theorem actually means, and then we'll go on and prove this theorem. So geometrical interpretation. So let's say I have a function so this is the this dotted line let this point be x1, let this point be x2. This dotted line, what does this represent? The linear approximation of f at x1. Okay, this is the linear approximation. So, and if you give any x, you will get a point on this line. So this tells us that the affine approximation or the linear approximation, the affine approximation or the linear approximation does not overestimate the original function. If you look at the inequality, it means that this represents the linear approximation, and it is always less than the value of the function at x2. So this is the value of, this is the value that the linear approximation will give, and this is the value of the original function, and the line will always be lower than the function itself. So this is what this theorem says, and it says that if this condition is true for all points, then the function is convex, and if the function is convex, the reverse is also true. So this is the geometrical interpretation. Now let's try to prove the theorem. Okay, so because it's if and only if condition, again we'll have to derive it in two parts. So the first part, let's assume that the function f is convex. Assume that f is a convex function. Okay, so f is a convex function. What does that mean? Is that f lambda dot x1 plus 1 minus lambda dot x2 is less than equal to lambda dot fx1 plus 1 minus lambda dot fx2 for all lambda belonging to 0 to 1. So this is what convexity of a function means. We can rearrange the terms and write it like f x2 plus lambda times x1 minus x2, correct? So less than equal to fx2 plus lambda times fx1 minus fx2. So this is just the rearrangement of terms. You can verify that. Okay. Now because lambda is a positive number, we can write it as so I just brought this fx2 on the left hand side, and also lambda, send the lambda to denominator because lambda is positive, so inequality sign doesn't change. So you can recognize this term as something, right? So what is this? This is the, so if, because lambda between 0 and 1, I can put lambda very close to 0, and if lambda tends to 0 from a positive direction, then this represents a directional derivative. So direction derivative of f at x2 in the direction x1 minus x2, correct? Which means it can be written as delta fx2 transpose x1 minus x2 less than equal to fx1 minus fx2. So which means fx1 is greater than equal to fx2 plus gx2 transpose x1 minus x2. So which proves our first assumption that if f is convex, then this inequality holds, correct? Now in the second part of the proof, we'll assume that let the inequality hold. Okay, which means fx1 greater than equal to fx2 plus gx2 transpose x1 minus x2. This is true. Now let's assume some point on the line joining s1 and x2. So let x equals x2 plus lambda times x1 minus x2, okay, which can be written as 1 minus lambda times x2 plus lambda times x1. Okay, this can be written as like this. Because the inequality is correct, we can write fx1 is greater than fx plus gx transpose x x1 minus x. We can also write fx2 is greater than equal to fx plus gx transpose x1 minus x. Okay, so this we can write. We'll multiply this by lambda, this by 1 minus lambda, and because both are positive number, we can add them together without changing the sign of the inequality, which means lambda times fx1 plus 1 minus lambda times fx2 is greater than equal to lambda times fx plus lambda times gx transpose x1 minus x plus lambda 1 minus lambda times fx plus 1 minus lambda times gx transpose x2 minus x1. So which a small rearrangement of the terms, you can see the lambda fx gets cancelled and we are remaining with fx. Then we have a term of fx transpose x2 minus sorry, this should be x, so x2 minus x, plus we also have a term with multiplied with lambda and gx transpose, in which inside it is x1 minus x minus x2 plus x. So x and x gets cancelled, which can be written as fx plus gx transpose x2 minus x plus lambda times x1 minus lambda times x2, correct? We can expand x now, so if we expand, it will be x2 minus You can see this is x minus lambda x1 minus 1 minus lambda x2 plus lambda x1 minus lambda x2. So we can see lambda x1 gets cancelled, and we are left with so this is multiplied by gx transpose plus fx. We are left with x2 minus x2 plus lambda x2 minus lambda x2. So which everything gets cancelled. So this term gets cancelled, which means we are left with fx1 plus 1 minus lambda times fx2 greater than equal to fx. And if we expand fx, we are left with lambda dot x1 plus 1 minus lambda dot x2, and which is given by fx1 plus 1 minus lambda times fx2, which means f is convex function. So we have proven both the parts, that if f is convex, then the inequality is true, and if the inequality is true, then fx is convex, and hence we have proven the theorem. So this is a very important theorem, and we should always remember this theorem. Remember this theorem, and because of its importance, we'll look at some of the interpretations, geometrical and other interpretations of this theorem, which help us appreciate this theorem much more. So interpretations of the theorem. Okay, so first interpretation is the same as we discussed earlier, that the linear approximation never overestimates the function itself. So let's just write it. Let C be a subset of Rn and f be a function from C to R, be a differentiable convex function on a convex set C then the first order approximation, or the linear approximation, or the affine approximation that we called it earlier, of f at any x1 belongs to C never overestimates So I'll underline this phrase, never overestimates fx2 for any x2 belonging to C. So just for the completion, you know this, we have discussed this, but I'll just draw it once more. So if this is a function and these are 2 points x1 and x2, this x1, this is x2. So the linear approximation of the function f hx equal to fx1 plus f dash x1 into x1 minus x, or x minus x1, It is linear approximation never overestimates the function itself at x2. Okay, so you can see the point, the value of the linear function is always less than the value of the function at x2. So this is what this interpretation means. Okay. So second interpretation can be seen, let's say it is a, let C be a subset of Rn, or let's say R. So let C be a subset of R. It's not Rn, it's R. That is a single real number. Be an open convex set, and f from C to R be a differentiable convex function on C. On C. Then consider 2 points, x1 comma x2 belong to C such that x1 is less than x2. So x2 is bigger. So please note, C is a single real number set. So we can have 2 points x1, x2 such that x1 is less than x2. So because f is convex, we can write this theorem, right? The results of this theorem, that is fx2 is greater than equal to fx1 plus fx1 plus x2 minus x1. We can also write fx1 is greater than equal to fx2 plus f dash x2 x1 minus x2. You can also write this. Which means f dash x2 into x2 minus x1. So remember, this is a positive quantity. It's greater than equal to fx2 minus fx1 and f dash x1 x2 minus x1. So how did we come to this point from here? So here you can just send fx1 on the left hand side. On the other hand, here you have to send fx1 fx2 on the left hand side and also multiply by -1 on both sides. So these two will exchange places. This inequality will reverse sign and this will become fx2 minus fx1. So this is what you have to do. You'll get this. Please note that these two are positive quantities. So these two are positive quantities, which means that the derivative of fx2 is always greater than equal to fx1. Okay. So one result that theorem automatically gives us is that if f is a differentiable convex function, f is a differentiable convex function of one variable, defined on C, which is an open set, then derivative f dash is non-decreasing. So if you keep on increasing x, the derivative will keep on increasing, it will never decrease. So that is the thing. And it turns out that the converse of this theorem is also true. Converse of this statement is also true. That is, if we have a function whose derivative, single real valued function, which single input real valued function in which if the derivative is non-decreasing, then f is convex. So this we can write. Okay, so apart from above two interpretations, there are two more interpretations related to convex programming problem. So let's discuss them now. So consider the convex programming problem given as follows, where you minimize fx over x subject to constraint x belong to set C, where f is differentiable. Now let x hat be some point belonging to set C. So then the optimal objective function value of the following problem, of the following new problem, minimize f x hat plus g x hat transpose x minus x hat such that x belongs to C, gives a lower bound. So actually if you solve this new problem, you get a lower bound on the above original convex programming problem. So this gives you a lower bound. How we'll look at it geometrically in a second. Gives a lower bound on the optimal objective function value of original convex programming problem. So let's say this is your original convex function, and this is its linear approximation. Let's say this is the set C. This is the optimal function value of original CP, and this is the optimal value function of the linear approximation. So you can always see that the minimum point of the new CP is a lower bound, gives a lower bound for the optimal objective function value for the original CP. Even though it's a crude lower bound, but still it's a lower bound nonetheless. So that is one more geometrical interpretation of the above theorem. Then apart from this, there is one more important relation that comes out of this theorem, which is again related to a convex programming problem. So consider a CP again. Here CP means convex programming problem, where we minimize f of x over x subject to constraint x belonging to some set C, where f is differentiable and C is an open convex set. Now we assume a point in C where the gradient of f vanishes. That is, let x star be some point in C such that gx star, which is equal to the gradient of fx star at x star, becomes 0. Then what we can say from the above theorem is that fx is greater than equal to fx star plus gx star transpose x minus x star, and as this is 0, this gives up fx is greater than equal to fx star, which means x star is a global minimum of function in C. So basically, if the gradient of the function vanishes at some point in the set, then that point is the global minimum. This is one more interpretation of that theorem. So here we'll end our discussion on convex functions. For now, we'll continue stating some theorems in the next lecture about convex functions, and we'll also try to start with the multivariable optimization in the next lecture. Till then, thank you.